When we are working with solutions of known concentration, we use molarity and volume to determine the number of moles. When we know the known concentration, we can use molarity and volume to determine the number of moles. Remember, in our stoichiometry roadmap, the moles is the heart of our problem, the want over given ratio. No matter what the unit is we're given, our job is to always turn it into the mole. Let's take a closer look at our first example, a titration problem, a solution stoichiometry problem. I'll read it for us. How many grams of calcium hydroxide are needed to neutralize 25 mils of a 0.10 molar nitric acid? Of course, we need to begin with a balanced equation. The first time I read through a problem, I really just ignore the numbers and try to pull out the chemistry. Calcium hydroxide, calcium with its +2, hydroxide with its -1, so when I write its formula, CaOH taken twice, is being neutralized by nitric acid. It came from 8. We know hydrogen is the first name of an acid. The polyatomic ion nitrate is NO3 -1. Formula for our acid is HNO3. The pattern of change shows a double displacement. Calcium goes to nitrate, hydrogen goes to hydroxide. The driving force is making water for acid-base chemistry. I'll write water is HOH, +1 with a -1, hydroxide and hydrogen written in their ionic form. And the salt produced is calcium, still a +2, nitrate, still a -1, so we come up with CaNO3 taken twice. I can clearly see if there's 2 base ions, we will need 2 as a coefficient in front of the acid. To neutralize 2 bases, we'll need 2 acid ions, creating 2 water molecules. The ratio here, a 1 to 2 to 2 to 1 stoichiometric ratio. Let's tabulate underneath what we know and what we're looking for. We want to know how many grams of calcium hydroxide needed to neutralize 25 mils of a 0.1 molar acid solution. Our given is the numbers that we have for the nitric acid. The want is our calcium hydroxide. Knowing that molarity is a concentration unit that describes moles per liter, our journey has us find the mole ratio of want over given. Let's start, as we always do, with what we are given. I like to write down, in terms of molarity, that we know we have exactly 0.1 mole of the acid, HNO3, in every liter of solution. The very definition of molarity, there's exactly 0.1 mole per liter of solution. If I multiply that by the volume in a liter, I was given 25 mils, 0.025 liters. Just set that on top of a 1 so I can clearly see the liter unit canceling. When the liters cancel, I'm at the mole unit. Liter units are gone. Molarity times liter pulls out a mole. We are at the heart of our stoichiometry problem, our want over given ratio. We want to know the base. Its coefficient is a 1. Every 1 mole of calcium hydroxide requires 2 moles of nitric acid. The want over given, I want the base from the acid. 1/2 is our stoichiometric ratio. Now what we've ended up doing is canceling the moles of acid. We're at moles of base. To land at a gram unit, mole times molar mass, again that's just an old stoichiometry problem. The very definition of mole is definition of mole is grams over molar mass. So I'll need to go to work adding up a formula weight for our base. Calcium has a molar mass of 40. There are 2 oxygens at 16 apiece and a couple of hydrogens. Molar mass of our base is 74. There is 74 grams of calcium hydroxide in every 1 mole of calcium hydroxide. Step 1, molarity times volume pulled out moles. Step 2, the heart of our problem, our want over given stoichiometric ratio. Step 3, to land at a gram unit, we multiply by the molar mass. And let's hit to reach a common answer. Please hit with me. 0.1 times 0.025 molarity times liter times the ratio of 1/2 times the molar mass of 74. The number of grams I find is 0.0925 grams of calcium hydroxide. It would take 0.0925 grams of base to completely neutralize 25 mils of a 0.1 molar nitric acid solution. Let's try another problem, and I'll read for us. How many grams of sodium hydroxide are needed to neutralize 20 mils of a 0.15 molar sulfuric acid solution? Again, the first time I do a read-through, I completely ignore the numbers and try to pull out the chemistry. What's going on in terms of a balanced equation? The first reactant I read is sodium hydroxide. Sodium is Na, carries a +1. Hydroxide is OH, carrying a -1. NaOH is a base. It's being neutralized with sulfuric acid. Ic comes from 8, so we look up the polyatomic ion sulfate. It carries a -2 charge. Acids always start with hydrogen, so when I crisscross, our formula for sulfuric is H2SO4. In an acid-base neutralization, we produce a salt water. Na goes to SO4, hooking by charge. We come up with Na2SO4, and when H goes to OH, we get a neutral water. Knowing that we have a diprotic acid, I can see that for every 2 hydrogens from the acid, we're going to need 2 base ions, and we'll end up creating 2 neutral water molecules. Stoichiometric ratio of a 2:1 to 1:2. Now that we have the chemistry set, we're ready to go back and just bookkeep what we know, what we're given, and what it is we're being asked to find. How many grams of sodium hydroxide underneath the NaOH? I know I'm looking for mass. The amount of acid says we have 20 mils of acid, and its concentration unit, 0.115 molar. The acid is the given. We want to know the base. I always start with our given and work to what we want. The very definition of molarity says that we have 0.15 moles of H2SO4 in a liter of solution. Moles per liter is our definition of molarity. We'll multiply that by the liters given to us, 0.02 liters, and I'll just set that on top of a 1 so I can see how the liter units are canceling. Molarity times liter pulls out the mole unit of our given. The given here is the acid. The heart of our problem says we want over given. The stoichiometric ratio, 2 moles of NaOH for every 1 mole of acid. A 2:1 stoichiometric ratio. We canceled moles of acid. Of course, liters were gone in the first step. We're now at moles of the base. To bring it out to a gram unit, our desired unit is grams of NaOH. Converting a mole into a gram requires a molar mass. Sodium, who has a weight of 23, oxygen is 16, and 1 for the hydrogen, gives us a molar mass of 40 for the NaOH. There are 40 grams of sodium hydroxide in every 1 mole of sodium hydroxide. Let's hit together and see if we get a common answer. Please hit with me. 0.15, the molarity of our acid, times 0.02, the volume in a liter of our acid, times the ratio of 2/1, times the molar mass of our base, sodium hydroxide, which was 40. We calculate 0.24 grams of NaOH would be required to neutralize the 20 mils of a 0.15 molar acid solution. 0.24 grams is our final answer. Our last problem under solution stoichiometry, and prior to doing some titrations, I'll read that for us. How many liters of a 0.5 molar hydrochloric acid are needed to react completely with 0.1 mole of lead 2 nitrate? Again, the first time I read through, I don't even like to bother with the numbers. Let's pull out the chemistry. First reactant I read was hydrochloric acid. HCl is our formula for hydrochloric. It's reacting with lead 2 nitrate. Lead carries a +2, nitrate, polyatomic with a -1, HCl plus PbNO3 taken twice. Double displacement pattern. H goes to nitrate, Pb goes to Cl. Based on charge, H is a +1, nitrate a -1, HNO3. Pb goes to Cl. Pb is a +2, Cl a -1, PbCl2, which, by the way, the driving force here would look like this as the precipitate. Lead chloride is insoluble. Balancing this, we need 2 of our acids on both sides of our arrow. A 2-to-1, 2-to-1 balances this equation. Now that we've got the chemistry, let's go back and put just bookkeeping. What is it we're looking for? What is it that we're given? It's asking me to find the volume, how many liters, of a 0.5 molar acid solution. The given is 0.1 mole of our lead 2 nitrate, not molarity, but the mole unit, the heart of our problem. Given lead nitrate, we want the HCl. The stoichiometry journey always begins with the given and heads to what we want. Let's start by writing the number, the unit, and the label of what we were given. 0.1 molar of lead 2 nitrate. We're already at the mole unit, so it's like starting us out in the heart of our problem. I don't need to exchange anything in that first step because they gave me a mole. Had they given me a gram or a molarity, I would have needed to convert out to a mole, but this problem was nice to us, got us started right away with that mole unit, heading directly to the ratio of want over given. We want to know the HCl. Its coefficient is a 2. Given the lead 2 nitrate, its coefficient is a 1. Moles of lead nitrate are canceling, and I'm at moles of HCl. From the information provided, we see that the concentration of this acid is 0.5 molarity. Thinking about the definition, molarity hides in its units, molarity, moles per liter. Our target here is the liter unit. We were asked to solve what is the volume. That's a liter. We have moles, it's sitting on top right here. Place molarity underneath it and we can cancel out to find liters. On the bottom, I will write that we have 0.5 moles of HCl in every liter of solution. I'm placing molarity on the bottom so that moles cancel and we land at a liter. The very definition of molarity, moles per liter. I'm placing the number on the bottom because I need it to cancel. I wouldn't want to place it on top or the unit wouldn't cancel out. On the bottom, I place molarity. The round buddy helps me see that as well. Moles over molarity pulls out liter. Moles over molarity pulls out the liter. Let's hit and see what we find for the volume of HCl. Please hit with me. 0.1, whoops, on, darn it, 0.1 moles of our lead 2 nitrate times the stoichiometric ratio of 2/1 divided by the concentration, 0.5 molarity, 0.5 moles per liter, and I find 0.4 liters of HCl. It would require 0.4 liters of a 0.5 molar solution of acid to neutralize 0.1 mole of our lead 2 nitrate compound. The term titration is an experimental procedure where we use an instrument called a burette to find something known as the equivalence point, where we have the exact stoichiometric ratio. Hang on.
Go to the cafeteria. Ho Yin Fong to the cafeteria, please.
Sorry. The word titration, it's used to determine the concentration of a particular solute in a solution. It involves combining a sample of the solution with a reagent solution of known concentration. What we know the concentration is always called our standard. It's our stock solution, might be another term you hear used. We made a standard solution in our Beer's Law lab. It's the one that we created of known value. Titrations can be conducted using any of our aqueous reactions. We first started this journey with precipitation reactions. We can conduct a titration with precipitation. We can conduct a titration with acid-base reactions, where water is the driving force. And we can also conduct a titration using a redox reaction. Any of our 3 patterns of aqueous reactions can involve a titration. The equivalence point is that point at which stoichiometrically equivalent quantities are brought together. That's simply known as the equivalence point. Where do we have a perfectly balanced equation, no limiting or excess reagent? In acid-base reaction, we use something called an indicator to help us see the equivalence point. Commonly, we've used phenolphthalein. It starts colorless and turns a faint pink color when we've reached the endpoint, or the equivalence point of our titration. Sometimes endpoints are not exactly equal to the stoichiometric ratio. Equivalence point is when we have our exact stoichiometric ratio being achieved. If we're using an indicator that overshoots a little bit the endpoint, that's when we see the indicator change color. Now, the best indicator is going to match the equivalence point. We'll talk more about that when we eventually in the springtime get to our acid-base chapter and talk about equilibrium. For now, the equivalence point will be helped to find using an indicator, typically phenolphthalein. Let's take a practice problem thinking about a titration using a precipitation reaction. It says a quantity of chloride ions in municipal water supply is determined by titrating with a sample of silver ion. The endpoint in this type of titration is marked by a change in color of a special type of indicator. Thinking about what this just said in terms of the chemistry, it says a chloride ion is titrated with a silver ion. Now generally we'll see the positive written first. An aqueous silver ion is being titrated with an aqueous chloride ion, and what will happen is a silver chloride will precipitate out. So a silver with a chloride precipitates to form silver chloride. Sometimes they'll even add an indicator to let you know that solid is forming. This white solid crystal that forms also lets us know the reaction has gone to completion. How many grams of chloride, that's my want, grams of chloride, are in a sample of water if 20.2 mils of a 0.1 molar silver ion is needed to react with all of the chloride? We're given information about the silver, a volume and molarity, and we want to know the mass of chloride. We'll start our journey with what we are given and head to what we want to know. The molarity of the silver was given as 0.1. Let's write that as the definition, 0.1 moles in every liter of solution. So when I multiply by the liters, 0.20, I said that backwards, 0.0202 liters, set that over a 1, so we can clearly see molarity times liter canceling volume and finding me the mole. Our heart of the problem is a nice 1-to-1 stoichiometric ratio. Every 1 mole of chloride ion requires 1 mole of silver ion. It asked me to find a mass, how many grams of chloride. So far we can see the liters have canceled, the moles of silver are gone. Mole times molar mass brings us out to find the grams of our chloride. The molar mass of chloride, I look on the periodic table, 35.5 grams of Cl negative for every 1 mole of Cl negative. The mass will not change based on loss or gain of an electron. So the molar mass of an ion is simply looking up to find Cl's atomic mass. Let's hit this and find a common answer. Please hit with me. .1 mole times our volume of O2 liters for silver, molarity times liters, times 1/1, the stoichiometric ratio, times the molar mass of 35.5 grams per mole for chlorine. 0.07171 grams of chloride ion would react with 20.2 mils of a 0.1 molar silver ion solution, 0.072 if you wanted to round a little different. If the sample has a mass of 10 grams, what percent of chloride does it contain? The percent of chloride could be found by simply taking part over the whole. 0.0717 grams of chloride divided by the 10-gram sample, expressed as a percent, will tell us out of the 10 grams, how many of those grams are being contributed from chloride ions. So while that answer is still on my screen, I'll divide by 10, express it as a percent, 0.7171%. So out of a water supply, we measured out 10 grams of municipal water. 0.71% of that are chloride ions. The next example will have us practice a redox titration. A sample of iron ore is dissolved in acid, an acid solution, and the iron is converted from a +3 to a +2. Friends, I need to adjust that in our note pack. Iron will start in iron ore as a +2, and it will go to a +3. We have to make that adjustment so our redox will actually balance. We then titrate 47.2 mils of a 0.0224 molar permanganate solution. Write the balanced redox reaction. So a practice looking at a redox. One of those, write the half reactions and combine back together. Let's do that together, please. Iron begins, oops, my pencil broke. Iron begins as a +2 and goes to a +3. We have to make that correction or we'll end up with electrons on both sides. To electrically balance this, we simply take, if a +2 goes to a +3, that's 1 electron to bring it back down to a +2 for both sides. There's the first half reaction. We have the permanganate, MnO4, that will go to a manganese plus 2 is the second half reaction. We will then add 4 waters to balance the oxygens, coming back to add 8 positive hydrogens to balance the H's. 8 H's, 1 Mn, 4 O's. On this side, we have a total of a positive 2. On this side, we're at a plus 7. So to the more positive side, I will add 5 electrons. Leo must equal Ger, so I can see that I'll distribute a 5 through the first half reaction and distribute a 1 through the second half reaction, and we'll simply add those back together and simplify. First half reaction shows 5 irons at a plus 2 from the top half, 5 electrons, 8 hydrogen ions, and an MnO4 negative 1. The combined reaction on the left side. The right side shows 5 iron positive 3s and 5 electrons from the first top half reaction. And on the bottom, we'll have an Mn plus 2 and 4 waters. The only thing I can see to simplify are the electrons, and here is my reaction for this redox. I knew it was an acid. I don't need to do the combining of the base ion. It's an acid solution. Our stoichiometric ratio, 5 iron plus 2s with 8 hydrogen ions plus a permanganate at a negative 1, produces 5 iron Roman numeral 3s, manganese plus 2, and 4 waters. We needed that part of the equation before I even cared about the numbers. We wrote a balanced redox reaction using the half reaction method. How many moles of MnO4 are added to this solution? That's coming back up here to the numbers provided in the problem. We were given volume and we were given the molarity. We're asked to pull out the number of moles. So, the very definition of molarity says there's 0.02240 moles of permanganate, MnO4 negative 1, per liter of solution, moles per liter, the definition of molarity. I'll multiply that by the volume, 0.0472 liters of solution. I'll just set that over a 1. Molarity times liter will find the number of moles of our permanganate. And let's hit that together. .02240 moles per liter times 0.04720, that's our liters, finds a mole number 0.0010, and I'll round here, 6. There's our moles of our permanganate. How many moles of iron 2 were in the sample? This is just looking at a ratio. From our balanced equation, I can see that for every 1 mole of permanganate, 1 mole, we have 5 moles of iron carrying a plus 2. So our given 0.00106 moles of permanganate times the heart of our problem, our want over given ratio. We want to know iron, its coefficient is a 5. Given the moles of permanganate, 0.00106 moles of permanganate, our want over given ratio, for every 5 moles of iron, we have 1 mole of permanganate. So the stoichiometric ratio of 5 over 1. This will convert from moles of permanganate into moles of iron. So I have that number from above still on my screen, so I'll go times 5. The number of moles of iron, 0.0052 and I'll just round here to be 3. This is doing a stoichiometry problem one step at a time. Step 1, molarity times liter. Step 2 is the heart of our problem, the want over given. We'll now take that mole number we just found for iron and convert it to a gram. 0.00523 moles of our iron. Using the molar mass of iron, 55.8 grams. And again, loss or gain of electrons will not change the molar mass. So simply finding the atomic weight of iron is finding the molar mass of iron plus 2. Moles times molar mass changes us to a gram. So while that number is still on my screen from previous problem, I'll go times 55.8. And my answer, 0.29498, I'll go 0.295 grams of iron plus 2. If the sample had a mass of 0.8890 grams, if our sample had a mass of 0.8890 grams, what percentage of iron was in this sample? Remember, we originally talked about iron ore, which is a rock coming from the earth. It's not pure iron. If the ore itself had an 8890 gram, 0.295 of those grams came from iron. Part over whole expresses a percent. Of the 0.8890 grams of the iron ore, 0.295 of those were coming from iron, expressed as a mass percentage as part over whole. So I still have the previous number on there. I can go 0.29498,112 because it's still sitting on my screen, divided by 0.8890 and express that as a percent. This iron ore sample was 33.18% by mass iron positive 2 charge. We balanced a redox reaction using the half reaction method. We did a stoichiometry problem, but step by step. Step 1 of stoichiometry, molarity times liter pulls out a mole. Step 2 is the want over given ratio. Step 3, we use that mole number and multiplied by molar mass to find our grams. The 3 steps to stoichiometry, just one step at a time in this problem. Let's practice an acid-base titration. One commercial method used to peel potatoes is to soak them in a solution of sodium hydroxide for a short time. That's like a concentrated Drano solution. It's going to remove the peel from them. So literally you can soak a potato, soak it in a strong base, and you can just literally spray off the potato peel. That saves time. The concentration of sodium hydroxide is normally somewhere between a 3 to 6 molar range. The sodium hydroxide is analyzed periodically. In one such analysis, 45.7 mils of a 0.5 molar sulfuric acid solution is required to neutralize 20 mils of the sodium hydroxide solution. What is the concentration of the base? Does it indeed lie between the 3 to 6 molar target that's allowed to spray on our food? So again, reading through this, it's a nice story, but read through without worrying about the numbers. Find the chemistry. We had sodium hydroxide being neutralized with sulfuric acid. Double displacement says we'll produce a salt, sodium sulfate, and a water, HOH. Balancing that equation, I can see this diprotic acid, H2SO4, will need 2 base ions to neutralize. 2 acid ions, 2 base ions will come together to make 2 waters. Now let's tally what we know and what we're looking for. We know it took 45.7 milliliters of a 0.5 molar acid solution to neutralize 20 mils of an unknown concentration of a base. Given the acid, we want to know the base. As usual, we start with given and work to what we want. 0.5 moles of sulfuric acid in every 1 liter of sulfuric acid. The very definition of molarity is moles per liter, multiplied by the volume of that acid expressed in a liter. So I can cancel the liters and end with a mole. Molarity times liter pulls out the mole unit. We're at the heart of our problem. We want over given. The coefficient of our base is 2. 2 moles of NaOH are neutralized for every 1 mole of our acid. Stoichiometric ratio is 2/1. We want to know molarity. Molarity is defined as moles per liter. Now watch what's happened so far. Liters of acid have canceled. Moles of acid have canceled. We're at moles of base. Knowing we're targeting molarity, molarity is moles per liter. Let's set the volume, that 20 mil, let's set the volume underneath and just set it up. Getting ready to hit for this titration problem. Molarity times liter of the acid, the want over given stoichiometric ratio. Putting the volume of the base on the bottom. Let's hit for the molarity of our base in moles per liter. So step 1, we multiply 0.5 molar times 0.0457 liters. Molarity times liter is a mole. Our ratio of 2/1, our want over given, divide by the 0.02 liters of base, and we have 2.285 molar NaOH. It's not lying within the range of 3 to 6 molar, I've noticed. Probably not going to peel a potato very quickly. Molarity times volume of the acid, our want over given ratio, divide by the volume of our base, and we end up with 2.285 molar, not within the range they were hoping for. Let's try a distributive practice problem. If 70.5 milligrams of potassium phosphate are added to 15 mils of an 0.5 molar silver nitrate, will result in a precipitation. Let's find a molecular equation. Potassium phosphate. Keep grabbing a pencil that's broken. Sodium is a +1. Phosphate, our polyatomic ion with a -3. Na3PO4. Being placed into a solution of silver nitrate, AgNO3, based on charge. Double displacement, silver goes to phosphate, sodium goes to nitrate. Sodium's a +1, nitrate a -1, so NaNO3, and silver phosphate, Ag3PO4. We'll need to balance with some coefficients of 3s. A 1 to 3 to 3 to 1, the way I have it written. Silver phosphate, by the way, will be our precipitate, Ag3PO4. We're given 70.5 milligrams, that's 0.705 grams of potassium phosphate. Why did I write sodium when it clearly says potassium? Easy to fix. The NAs have now become a K. Sorry. Potassium phosphate, K3PO4. 0.0705 grams of potassium phosphate are added to 15 mils of an 0.5 molar silver nitrate, resulting in the precipitate silver phosphate. Our molecular equation, a 1 to 3 to 3 to 1 ratio. What's our limiting reactant? Well, I know that I need a 1:3 mole ratio, and we're being asked to calculate the theoretical yield of the precipitate that forms. So what we want to know is the grams of our Ag3PO4. Let's set up a first journey where we start with 0.705 grams of K3PO4. And a second journey will be taken from silver nitrate. Our target will be silver phosphate. We can find the theoretical yield by working out two separate problems, knowing the smaller of our two answers will be the limiting reactant. So I'll need a molar mass in my first conversion of potassium phosphate. There's 3 potassiums at 39 apiece. Phosphorus adds 31 more, and 16 times 4 for the oxygen, I get 212. So 1 mole of K3PO4 would weigh 212 grams of K3PO4. The heart of our problem is a want over given ratio. Every 1 mole of silver phosphate for every 1 mole of potassium phosphate. Our want over given is a 1-to-1 ratio. To go to a gram of our precipitate, silver phosphate, I'll need a molar mass to convert out. Silver is 107.9. There's 3 of those, plus 1 phosphorus, plus 4 oxygens. 418.7 grams for every 1 mole of silver phosphate. Divide, ratio, multiply. Let's solve for this problem and see what the yield is. 0.705 grams, divide by molar mass, 212 of our given potassium phosphate. We have a 1/1 ratio, so I'll multiply by the target, 418.7 grams, the molar mass of silver phosphate. Maximum yield here, 0.139 grams. Let's see what we get from the other reactant, the silver nitrate. Here we were given 0.5 moles of silver nitrate per liter of solution, the very definition of molarity, moles per liter. Multiply by that volume, 0.15 liters, and we can cancel those liters, bringing us directly to the heart of our problem. We still have the same target, 1 mole of silver phosphate for every 3 moles of silver nitrate. Want over given is 1/3. Times the same target molar mass, 418.7 grams, will take us out to that precipitate unit in a gram. Molarity times liter of silver nitrate gets us to moles. A want over given ratio times the molar mass. Let's solve for the grams of silver phosphate from the silver nitrate. 0.05 times 0.015 is molarity times volume. The ratio of 1/3 times our molar mass of 418.7. 0.105 grams of silver phosphate. I can clearly see, comparing these two answers, the first answer 0.139, the second answer 0.105, the smaller of the two answers is my theoretical yield. Sometimes you hear us call it the maximum yield. It's the most I can make is the smaller of those two answers. And to answer this question, the limiting reactant is the one that gave me the smaller one. Reactants are on the left. The silver nitrate was the limiting reactant. It gave us the smaller of the two answers. Potassium phosphate is an excess reagent. Silver nitrate is the limiting reagent with the maximum yield 0.105 grams of our precipitate silver phosphate.